Swayam Prabha. Digital India. Educated India.
Good morning to one and all of you. I am honored to introduce you to Dr. P. Venkatakrishnan. He is a professor at the chemistry department, and as you know, he is also he is a coordinator here at RSIC. So his lines of research and interests include molecular electrical components, organic electronics, and macrocyclic and synthetic chemistry. He finished his PhD at IIT Kanpur, and he joined the chemistry department after 5 years of postdoctorate in France and Alberta, Canada. So we are delighted to have you here, sir, for our first lecture by you. And so thank you, sir.
Thank you. Thank you. I hope everyone is here. Someone is not stuck there. Okay. So today what I planned was, I don't know, we'll be able to go through all the slides. It's not so important. What I would like to give you is the kind of feeling how your fundamental concepts are useful in sort of developing materials, okay, which are useful or have application in certain fields. So that is the summary that I would try to give you at the end of this lecture. Let's see if we can go till the end, okay. So title as such, it starts with photochromism as a word, and then you also have organic materials. So it's something of type materials, but it belongs to an organic category. No inorganic chemistry involved, right? And we are talking about something very reversible. So there is some physical chemistry component involved. You will start from a starting material, say A, getting converted to something product, which is B, and then B doesn't stay there, it would come back to A also. So that is the kind of phenomenon we are going to talk about. And what is reversible here? It is the color change that is reversible. So you start from a colorless A, right, precursor, you would generate a colorful B, or of different color, for example, then it would come back to A, which is colorless, or to its native color. So this is the reversible color change we are talking about. And what we are also going to use to induce this reversible colorful transformation is with light. Okay. So you are basically going to involve light. You are going to use organic materials. You are wishing to induce a reversible color change, right? All of this phenomenon put together is called as photochromism. You would have seen this word somewhere. Where is it being used? Photochromic materials, photochromic lenses. Yeah, now I get the code. That is the code that you want. So when you have photochromic lenses, so there is a film that is coated on our, optics surface. When you are exposed to sunlight, you would see the glass undergoing a colorful, it achieves a colorful state, and upon exposure to sunlight basically, and you come back to room, it comes back to its native color, which is colorless and transparent, we are able to see, right? So these materials are useful in that application. Other than that, there are a lot of fancy applications involved with such materials. You would see kids, or maybe you wearing a t-shirt which, some labels, and when you are within the house, you don't see the color, but when you go out, play in sun, you change its color, say, have fun, play with colors and so on and so on. There are a lot of, this is for fancy application, okay. So these are the materials that we are going to talk about with different classes. But I would talk about one particular class to give you a kind of feel as to how organic chemistry, the fundamentals that you have learned, could be useful in developing such materials. Okay. So this you must have seen, I think, the popular Jablonski diagram. Professor Prasad would have introduced you to this kind of a diagram. Did he? No? Has anyone talked to you about electronic excitations? So you are introduced to it. Who talked to you about it? Professor Rangarao sir. Okay, good. So you have electronic transitions involved, and in an organic molecule typically what will you have is a single bond. You will also have double bonds having one sigma and one pi. You can have triple bonds where one sigma bond and two of them pi bonds, and any organic compound you take, you will also have heteroatoms such as oxygen, sulfur, nitrogen in them, and they will have their pets which are non-bonded electrons associated with them, and these are the typical type of electrons that you would see in an organic molecule, right? So those are sigma bonds, those are pi bonds, those could be non-bonded electrons. So there are three types that you can see, and when you shine a light of appropriate wavelength, which one is stronger in this case, sigma, pi or non-bonded? Energy wise, which is a strong bond? Sigma bond. Sigma bond is a strong bond. So if, like sir talked in the previous lecture, if you have to dissociate them homolytically, you have to provide a bond dissociation energy of that particular bond, right? Carbon-carbon bond dissociation energy, if you provide in terms of light, then you would be able to dissociate the carbon-carbon bonds. Then homolytic fission is possible. You can create radicals. People are interested, whoever is interested in radicals, they would capture them and then look at their kinetics, rate of reactions, how they react, what kind of products that they can give is their interest. Okay. So if you don't deal with the sigma, let's say we want to talk about pi, electron alone you want to excite or take it to a higher energy level, these electrons, then what would you do? You have to use a lesser energy wavelength when compared to that of used for cleaving a sigma bond, right? So if you go for pi electronic transitions, then you would use a lesser energy light. You want to promote an electronic transition with the non-bonded electrons, then you would use even weaker energy of light, so that you would be able to transfer. A simplest example that I can give you is formaldehyde. Very simplest molecule, right? How many number of pi, how many number of sigma, and how many number of non-bonded electrons are situated in this molecule? 3 sigma, 1, 2 and 3, 1 pi, and there are 4 non-bonding electrons, right? This we call as rabbit ears, because this is the orbital that it is located with itself, right? So these are 3 types of bonds. So if I am shining this molecule to a higher wavelength of light or high energy beam, what can happen is all the transitions are possible. All the transitions are possible because sigma is the highest energy, and if you shine it with a high energy wavelength of light, you would excite this electrons, you would also excite this electrons, you would also excite this non-bonded electrons. Correct? But keep in mind, if you are the sigma electrons, if you want to excite, right, and these are associated with the higher energy, means the absorption, sigma electrons to get excited go to, sigma is a filled orbital, it has to go to an anti-bonding sigma star, right? So if the electron has to be promoted to sigma star, then the energy that you require is corresponding to the wavelength range, which is typically around 200 nanometers. Typically around 200 nanometers. What if you use less than that? Let's say 180 nanometers. then suddenly you are going to dissociate. After promoting an electron to the excited state, you are going to completely dissociate. You are taking it very far, right? So in that case, you may end up dissociating this sigma bonds. So that can happen. Well, where do these pi electrons transition? The energy required to excite a pi electron lie. If you look at that, for this typical compound, it would lie somewhere between 240 nanometers. Okay, so it is slightly lesser than what you had used for a sigma to sigma star electronic transition. And this is a high energy, we said. So it is very difficult to characterize these transitions using typical UV visible absorption spectrometer that is available in market. Okay, because they will start typically from 250 nanometers over and above. You cannot use 210, 200, 180, 190 is going to be very, very challenging. Because you need vacuum ultraviolet, because we know that oxygen absorbs in that range. That would also interfere when you are doing a UV visible absorption. Okay, so that is the problem. So sigma to sigma star transitions, we mostly don't worry. If you are typically looking at formation of radicals, studying radicals, then one would be more interested in using or cleaving sigma bonds. But the transitions of pi to pi star is noticeable, because we said it lies in the range of 240 and so on. Non-bonding electrons would absorb or get excited in a region between say 260, 280 nanometers is where you would start to see these non-bonding electrons undergoing a transition, right? Pi, when you excite, it goes to pi star. Where does this non-bonding electrons go? Where do they go upon excitation? Because they are not bonded. That's why they are non-bonded electrons. They are freely available, easy to excite. But where do these electrons go? They would either go to pi star or they would go to sigma star. So you will have N to pi star transitions, N to sigma star transitions possible. N to sigma star transitions are little more higher energy than the N to pi star transitions. Okay. So for a simple molecule such as this, you will see this many transitions possible. And what this diagram typically represents is, you have a molecule in the ground state. Ground state means now under thermal mediation alone, you have thermal energy alone available for the molecule. Now if you shine it with light, these electronic transitions happen, and these electrons would go from S0 state to S1 state, and in the S1 state, now you have taken this to a higher energy state. So this is again a singlet. S means a singlet where spins are paired. Ground state also spins are paired, and the excited state also spins are paired, but these their energy would be a little higher than what it was in the ground state, right? But this transition typically from S0 to S1 is damn fast. If you shine a light onto the particular organic compound, the electronic transitions before we blink our eyes, they happen in a time scale of typically few femtoseconds, 10 to the power minus 15 seconds. These electronic transitions would just like that happen. So excitation is the fastest process. When you shine with the light a molecule, then you would see these electrons undergoing excitation in such a rapid manner. Now there are higher energy levels beyond, over and above S0. What could they be? S0 and then, S0 and then S1, right? S1 state, over and above, you can also have S2, you can also have S3. Those are all higher energy levels. So when the electrons are pumped from here up to the higher energy state, what you will see is the electrons are slightly going higher than S1 depending on the energy whatever you provide. They would internally convert and come back to, or relax, come to the S1 state, which is the lowest energy excited state, right? So this is the ground state, and from ground state when electrons are excited, they go to the lower energy excited state, reach the higher energy, of course they relax, come back to the lowest energy excited state. That process is called internal conversion. Now from the S1 state to come back to S0, it has to come back to its native state. But while coming back to the native state, they would release the energy that it has acquired either in the form of light or in the form of heat. When it releases the energy in the form of light, we are able to see that as fluorescence. So you say the compound is emitting, wow. Emit means it emits from its S1 state, from the excited state, whatever light energy it has absorbed. Whatever light energy it has absorbed, it is giving you back quantitatively 100% in the form of light. Then you say that process is very efficient. The quantum efficiency for that process is 100% in terms of, or if you want to convert it as numbers, you'd say as unity. Yeah.
Sir, when you said at times it goes to X2 and then relaxes back to S1, does that energy also come into fluorescence or phosphorescence?
Yes. Oh no, when it relaxes, it is an internal conversion. That time scales are typically in a range of, because it went up to femtoseconds, right? So that process would be happening in picoseconds. What basically happens is, you have molecule like this. When it goes to excited state, it goes to excited state like this, which means no conformational change happens in the molecule. Before the molecule realizes, it's already in the excited state. Because the acquired energy has gone to the excited state. Then it sees, whoa, relaxes. Relaxing process is what? The required energy is used in the form of some deformation in the molecule. So there can be nuclear displacements. In excitation, there is no nuclear displacement. Moment it goes to that S1 or slightly higher energy levels, that's when it realizes and starts to do the nuclear displacements. And when that nuclear displacement happens, that's when it starts to release the light. It will undergo conformational change. And that conformational changes are responsible, or the ways by which the molecule releases energy. What could be the conformational changes? Vibrations, rotations, right? So for example, typically this molecule is, the carbon here is sp2 hybridized. When it goes to excited state S1 and higher, moment it undergoes excitation, there will be no nuclear displacements. Still it is in sp2. But when it starts to do this nuclear displacements, it may achieve sometimes sp3, which you may not realize, right? So this molecule, the excited state could be in sp3. So what it means is you will have this pyramidal structure, the tetrahedral structure with oxygen pointing upwards and the three atoms are connected like this, radical located on carbon, radical located on the oxygen and so on. So it will undergo conformational changes. Any molecule, the excited state, in a time frame of about few picoseconds, you would see all these conformational changes. You can study this using time resolved infrared spectroscopy.
So when it comes back to S1, it will be...
When it comes to S1, that's when it starts to emit light in the form of fluorescence. The heat energy that we cannot see, unfortunately, is assumed as a non-radiative decay processes. Fluorescence is a radiative decay process, and the other process that can happen in the form of heat is assumed as a non-radiative decay process, meaning that the remaining ones immediately goes to triplet state and you may start to emit from the triplet state. That is called phosphorescence. So time scales for fluorescence is in nanoseconds. So you will see light emissions in the time scale of nanoseconds. So before that you can't see. I mean less than in the time scales of picoseconds or femtoseconds you will not be able to see.
So at S1, will they be back at their original shape or will the conformation stay?
In the S1 state.
After getting excited and coming back to S1, will
Yeah.
the conformation stay or will it go back to the...
The acquired energy will be there, but it will not be to an extent that you had acquired before, because in the process from femtoseconds to nanosecond you had already lost something, right? Some energy in the form of heat, which is due to vibrations and all that. But when from here to here, the molecule starts to give out the light, because that much energy only you have provided. The energy that the molecule can absorb is just the energy between S0 to S1. That much only it can take. The molecules are not greedy. But you may pump in more energy than the molecule requires. But molecule would take up only the required amount of energy for the transition, right? Yeah. Phosphorescence is an emission process from the triplet state. Triplet state means how the spins are. They are not anti-parallel like in S0 and S1, but they are going to be parallel. So spins have to flip, one of the spins have to flip and then become parallel. And that state is called an inter-system crossing, because we say singlet is one state where spins are anti-parallel. Triplet is a state where the spins are parallel. So it has to do a spin inversion in order to go from S1 to T1. From this, in this state, right, it has to come back to again spin being anti-parallel, and that process is involving with phosphorescence. Why should the? So in a longer time scale, these things would happen. So if you will have it in the form, let's say you are having it in a time, I said fluorescence is in nanosecond time scale. In the case of phosphorescence, this is in few microseconds to milliseconds to these days people are achieving up to seconds. So the time scales are completely different. Any organic molecule you take, you will be able to notice the fluorescence mostly. It is very difficult to observe the phosphorescence as such, which is from the triplet excited state. There are certain functional groups which would promote this intersystem crossing, thereby singlet to triplet could be easily achieved, and you will, in those cases, you will see phosphorescence emission coming out. Okay, because detectable at room temperature is very challenging. So people used to detect this phosphorescence at a very low temperatures up to 77 Kelvin or maybe 100 Kelvin temperatures. Every molecule you would see the phosphorescence with a very weak emission to a strong emission depending on which state it is preferred by the molecule. Some functional groups would promote this 100%, some functional groups would allow the spin cross to happen and emit from the triplet state up to 75%, 60% and so on. Many of the organic molecules you may not even detect. So people are these days are developing phosphorescent based organic molecules which can quantitatively emit from the triplet state but at room temperature, not at lower temperature. So that is the challenge that scientists are facing now. They are developing materials which can do the phosphorescence at room temperature. So the design aspect, how to conformationally lock the molecule, make them emit and facilitate the intersystem crossing quantitatively. And because the spin population wise, if you see, triplet will have the more spin population. Singlet can have only one, right? But triplet this way also, this way also, this way also, will have combination. So we will have about 75% of spin population coming from the triplet state, 25% only from the singlet state. Any kind of device that you develop where you are looking at light emission, people would like to harvest the 75% which otherwise is unnoticed, right? So this is where the research emphasizes in these days that anyway we have plenty of molecules which can give emission from the singlet excited state. Okay. So with this brief introduction, yeah, please.
So, why does the molecule see the need to convert from the singleton state to the triplet state?
Why should the molecule?
Transit from the S1 state to the
Triplet
triplet state.
state, see, under certain circumstances, the radical, which means you are having, when you are having triplet means you generate spins being parallel, right? So this is a kind of characteristic for the molecule to behave as a radicals. Two centers somewhere in the molecule where the spins are parallel could be stabilized by that system. So under such conditions, this paired scenario in the excited state, because it still has its energy. So in that energy that it has, it would also do the spin inversion, and if that being stable, you will start to see the triplet being populated more and more. This is common in systems wherever carbonyls are present, sulfonyl groups are present, okay, and heavy atoms are present where spin orbit coupling is, spin orbit coupling have you heard of? Spin orbit coupling. Any heavy metal complexes, if you look at organometallics, they would promote spin orbit coupling. Similarly, you will also have such organic molecules having bromine atoms or iodine atoms within themselves. Such heavy atoms are present in the molecule. You will facilitate spin orbit coupling, and then you will start to automatically populate the triplet state. In some cases, you need to drive, some cases the molecule, depending on the functionality it has, it would move to the triplet state. Okay, so which means the biradical state is more getting favored under circumstances with that energy. So that is popular. Another important point, I don't know whether you have come across or you have heard about it, if the difference between the singlet and the triplet is quite closer, and that is one of the engineering ways. When you design a molecule, you can derive the singlet excited. Okay, I will ask you this question. How do you estimate this S1? If you want to know the S1 energy level, how do you know? How can I know the singlet energy level? Say it again, one after the other. Huh? Yeah, measure the fluorescence, because the emission is going to happen from here, correct? If you record an emission spectrum and take the maximum point, peak maximum, then you will be, because you on the x-axis you will have wavelength, you convert the wavelength to energy, and you know how much is the singlet excited energy level for that molecule. And how much light you should give it to the molecule, how do you know? How much energy a molecule is going to absorb? How much should I provide? How do I know?
So we need to know exactly what we need to do to get it as one. So HMU will, so that mu will have to.
How do you know? What is the experimental technique you would use? Yes, 0 to S1. Yeah, but you can record a UV visible absorption spectrum. So it gives you a profile of the molecule up to what range it absorbs, starting from an ultraviolet and then visible. If it has a whole range of absorption, then you can take any point in that whole range, then start exciting, right? And the usual practice is, if you have the UV visible absorption, absorbance A, and you plot it with lambda here, nanometers, if this is the absorption spectrum for a molecule, the usual practice is the minimum energy, right, at which the absorption is going to start. That is the point if you supply, that is enough. That much amount of energy, if you supply for a molecule, it's going to absorb. Because it's the minimum energy that is required for a molecule to absorb. Tail end of the absorption spectrum. Maximum, yes sir, can I absorb, can I excite here? Yes, you can excite. Can you excite here? Yes, it is still possible because molecule absorbs in that region. Can I excite here? Yes, possible. But beyond this, where the absorption becomes flattened, beyond this you cannot excite. Right? So the minimum energy that is required, that will give you a difference between S0 and S1. So that is called the energy gap for the molecule, or optical energy gap, which is the highest occupied molecular orbital. You must have studied in ethylenes.
So the other peaks are other singlets.
Which are the other peaks?
The other peaks will be S3, S4.
Yeah, correct. It could be SC, S3, S4, and the broadening reason you know, right? Broadening reason you know. Why is the absorption spectrum broad? See, atomic absorption, if you record, they are going to be in lines actually. Same way, absorption, lambda, nanometers. So if you record atomic absorption, you will see lines. For example, sodium vapor lamp, will have emission lines very sharp. What is that noise? Where does that come from? Atomic absorption lines are sharp. There is only one atom. But when you talk about molecules, there are several atoms in them, and hence
energy is lost to collisions, and then because of that, what we get out is, we might not get the exact number, but whatever the maximum is, that's like.
Yeah, but when you have multiple atoms, you will talk about diatomic molecule, means you will talk about vibrations coming into picture, the rotations coming into picture. So when you have multiple atoms connected to each other forming a larger molecule, you will have scenarios such as not only electronic energy levels, you will also have vibrational energy levels, which is like that. This is the S0, let us say, this is S1, right? You will also have their vibration energy levels here. Within vibration energy levels, you will have rotational energy levels, because those would require only smaller energy. So within the vibration energy levels, you will have rotational energy levels, right? So in a ground state, an electron need not be exactly in S0. Some electrons could be there as well. You will see some electrons are in vibration energy levels located at different points, right? So when electronic transitions happen, they could be promoted from here to higher vibration energy levels, or like could be S2, and S2 will also have its own series of vibrational and rotational energy levels. So it has to come back to S1, relax, come here, and then relax all the way, come to ground state. So the combination of electronic transitions, right, will give you information about the vibronic energy levels also. So these peaks need not necessarily be from S2, could be from S2, but it could have been from one of the vibration energy levels, it comes down and then relaxes. So by knowing each peak value in the absorption spectrum, you will be able to understand the vibration energy levels, gaps between the vibration energy levels, right, how they are. So actually these are called as vibronic pattern in absorption spectrum. It is very rare to see such scenario. But if you are seeing it, you will be able to calculate all that information. Okay. So S1 you can calculate. T1 how can you calculate? Like you recorded the fluorescent spectrum, you should also record a phosphorescent spectrum at 77 Kelvin or 100 Kelvin if the molecule shows you the phosphorescence. From the peak maximum of phosphorescence, you can calculate the triplet energy levels. But triplet energy levels are supposed to be lower than singlet or higher than singlet? In terms of wavelength, can you guess? In terms of wavelength? So absorption is like this, fluorescence then should be at a higher wavelength or the shorter wavelength? Because it has lost its energy. The excitation, after excitation, it has lost its energy. It has come to the S1. From S1, it has to come to S0. So it would require lesser energy. So in that case, to a longer wavelength, it has to shift. So you in the absorption, if you record the absorption spectrum, let's say this is absorption spectrum. Fluorescent spectrum would be something like this. At a higher wavelength range, and phosphorescence. Look at this diagram. It should be in the same place or should be shifted further? Should be shifted further because during the spin flip process, it has lost some energy. Right? So spin flipping involves the energy. Again, that is a loss process, energy loss process. So phosphorescence should come at a much longer wavelength or a higher wavelength. So energy wise speaking, if you want to place these in the energy levels, so you will have S0, S1, so you will have T1 here. If you somehow engineer the molecule to bring these triplet energy levels or reduce the singlet energy levels so that the S1 and T1 could be closer, then the electrons could jump from S1 to T1. If it is closer, let us say, you have made some molecule like this where the S1 is closer, or you have lifted the energy of the triplet and thereby you are decreasing the energy gap between S1 and T1. The electrons need not stay in T1, it can come back to S1 because that energy gap is available, that much quantum of energy is available for it from the environment. So a simple thermal energy could undergo a reverse intersystem crossing from triplet to singlet, and that species you will see with a delayed fluorescence. Will come back from again S1 to S0. Okay. There is a prompt fluorescence which upon excitation immediately comes back to the ground state as 0 by giving light out. It can come back late because it has to undergo a spin flip, goes to triplet state, and it cannot stay there. It doesn't mind to do an endothermic process, uphill process. It's okay. That energy it acquires from the temperature. So it goes to S1, and from S1 it can come back to S0, giving you a delayed fluorescence. So by comparing the time scales, lifetimes, if you measure, you would know which one is a prompt fluorescence, which one is a delayed fluorescence.